We're good? All right, yeah. So I have a suspicion that the audio in this video is going to be like super loud. So in the future, I apologize. Let me begin with a word of prayer. Dear Heavenly Father, we thank you again for this time that we have to meet together to study your creation. Just pray that you'd guide our steps and just help us to understand more about trig substitution today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me show you a kind of a low-tech application of trig substitution. So here's one, example one. Suppose you're up against the integral of dx over x squared plus 4x plus 5. All right, now this doesn't seem to quite fit the bill, right? Like it's not a square root, but nevertheless, trig substitution is going to be helpful here. But before that, I need to take a walk down memory lane with you and remind you that we know something about quadratics, right? And so a quadratic, you can complete the square on it, right? So this is really dx over x plus 2 quantity squared plus 1. All right? So what we're really looking at here is something of the form variable squared plus 1, right? So then I go and I look at I think back to which is the right trig substitution. So apparently a tangent substitution is the right one to go with here. And so what we're going to do for this is we're going to let x plus 2 equal to tangent theta. And if we do that, we're going to be off to the races here. Let me show you how. Well, then dx is secant squared theta d theta. And what happens with x plus 2 squared plus 1? Well, let me just do it in the integral for a change. I've been doing a lot of the algebra on the side, but you could either do the algebra in the integral or off to the side, but you need to do it somewhere, right? So x plus 2 squared, that's tangent squared theta plus 1. What is tangent squared theta plus 1? Secant squared theta. So what are we looking at here? Yeah, we're looking at the integral of d theta, also known as theta, plus a constant, which if you solve for theta, what you got? You got inverse tangent of x plus 2 plus a constant. So here's a neat thing. If you forgot about the integral of 1 over something squared plus 1 being inverse tangent, trig substitution will derive it for you. If you understand trigonometric substitution properly, you can derive all the things that you didn't know from calculus 1. Here's another one. Suppose we're up against the integral of like dx over the square root of, let me make this one a little bit simpler. No completing the square this time, but something like, say, 9 minus x squared. So like there's one school of thought here, which is you just basically make a u substitution, and you know stuff from calculus 1, so you can do it, right? But there's another way to do this here. What should we make? What's the trigonometric substitution we could do? X equal to what? Yeah, 3 sine theta, right? So then dx is 3 cosine theta d theta. And what do we got? We're up against 3 cosine theta d theta divided by the square root of what? 9 minus 9 sine squared theta, right? But do the algebra, what you got in the bottom? Square root of 9, right? Times what? The square root of 1 minus sine squared theta. Because I can factor the 9 out, right? But what is 1 minus sine squared theta? This is straight up cosine squared theta, right? And from the context here, we know that that has to be equal to cosine theta. So what you got here then is the integral of, what's the square root of 9? 3. 3 over 3, 1, right? So Sorry, this is kind of boring. It's the same thing that happened last time, isn't it? So this is, what do we got? I feel like I have neglected a 9 somewhere. Is that really it? Oh no, we're fine, Never mind, my bad. I'm trying to talk myself into this being wrong, but I shouldn't. So that is, we can all do that integral, right? I think we can do that one. Theta plus a constant, and then, but what is theta here? See, we've got sine theta is x over 3. So what did you say it was? Theta is what? Inverse sine of x over 3. And there you go. That's the integral, right? Yep.
So did you put under 3 cosine theta d theta, you put square root of 9? Is that because that's what the form is supposed to be in? Because you chose x equal 3 sine theta.
Yeah, that's because I want the substitution to match up with the 9 that's already there. So I got to put a 3 there because I'm going to square it to get a 9. And then since there's a 9 in both terms, I can factor it out. And then, square root of a times b is the square root of a times the square root of b. So like square root of product is product of square roots.
So when you chose x equals 3 sine theta, that covered both the 9 and the x squared, I guess.
Well, I mean, yes. Yeah, I mean, that's the way you could say it, sure. Now, we could ask you this integral in calculus 1, right? Why? Because you can just make you can identify that this is really the integral of inverse sine, right? Like the way you could do this in calculus 1 would be something like this. You factor the 9 out, right? Well, so factor a 3 out, right? This is really 1/3 dx over the square root of 1 minus x over 3 squared, if you think about it. So then you make a u equals x over 3 substitution, and this gives you then du is, 3 du is equal to dx. So when you take that, you get 1/3 integral of 3 du over the square root of 1 minus u squared, right? Which then gives you, the 3's cancel, and you get inverse sine of u plus a constant, which then gives you inverse sine of x over 3 plus a constant, right? So here you go. This is the calculus 1 way of doing this problem, right? But that requires you to know in your heart that the integral of 1 over the square root of 1 minus x squared is inverse sine, right? Do you know that? If you know that, great. If you don't know that, if you learn trigonometric substitution, you can derive it. All right, so my first 2 examples, do you really need trig substitution for these? Not really, right? These are really elementary integrals. We could have done with like inverse trig stuff from last semester. Let's work on one that's genuinely trigonometric substitution. So these are courtesy of Dr. Sprano. We're going to look at the integral. Actually, can I erase? Let me just take a breath here. I'm gonna come back to here. I'm gonna start working here again. Well, I just don't know how much trouble that problem is. Let's start here, just in case it's a lot of work. I'd like to be able to fill a couple boards with it, just in case. Show of hands, who is not comfortable with completing the square? Some people, right? So we need to, if that's the case, we should, try to hit some more examples with that. I'll come back to that. That's not in this example, but let's see here. Example 3. The integral of the square root of 9x squared. I was about to make that 9x to the 4th. That would be a different kind of problem. Like, I don't know if I can do it kind of problem. So here we go. Square root of 9x squared minus 4 over x. So what? First of all, it's got a square root, so it kind of yells at you, try a trig substitution, right? Which should we make here? What do you guys think? Secant theta? Let's see here. So what secant theta equal to what are we talking about here? So you say again? 3x equals to what? Secant theta? 4 secant theta? 2 secant theta? Well, there's a lot of options, aren't they? Which one should we pick? I think the 2, and let's see why that works. So if we make this 2 secant theta, then what we have, if we look at 9x squared minus 4, that's equal to 2 secant theta squared minus 4, right? Because 9x squared is 3x squared, so that's... Let me one more step. Sorry, guys. One more step. So this is 3x squared minus 4, right? Which by our substitution would be 2 secant theta quantity squared minus 4. We can factor the 4 out, and we get secant squared theta minus 1, which of course is tangent squared theta. So that's nice, because this, under this substitution, we're looking at the square root of 4 tangent squared theta, right? What's my dx? So look, x is equal to 2/3 secant theta, right? So that makes dx 2/3 secant tangent. So this is all just, you know, the details of the substitution here. Now x apparently is 2/3 secant, so I got to put that downstairs, right? 2/3 secant theta. And then my dx was 2/3 secant tangent, yeah? Let me come down here and increase my font. So the 2/3 are canceling, yeah? That's nice, yep.
When you factored the 4 out, what happened to the 2?
2 squared is 4, so there's a 4 in both terms.
Okay, I see what you're saying.
Uh-huh. So these 2/3 cancel, right? And what we got? We've got integral. What are we up against here? Tangent, the secants cancel too, don't they? Isn't that nice? See that? Cha. That secant's dead to us. Let's see here. Such violence. Let's see here. 2. We have 2 tangent, also known as tangent squared theta d theta. Can we integrate this? Yeah.
Change the tangent to secant squared minus 1.
I like that. So we've got 2 times secant squared theta minus 1. Is that right? I got to think about that for a second. Remember, tangent squared theta plus 1 equals 6. Yes, okay. I don't know, for me, like logically, I just have the tangent squared plus 1 equal to secant squared as like primary in my brain. So I have to like process from there. Now, what do you guys think? Is this right or wrong? How many decipoints do I lose on the quiz for this one?
D theta.
That's right, I lose 10 decipoints for not writing d theta. Thank you. So it's not the end of the world, but I will dock you on it because that d theta is not decoration. It needs to be there. Why? Because we're doing things with that, and not writing it means you're going to forget to do it. Some of you have gotten a bad habit of doing integration in Calculus 1 without writing dx, perhaps, right? There's a subset of Calculus 1 teachers who are like super cool and like, yeah, whatever. They've got the main idea. I'm not going to sweat them on the notation. It all comes back to get you eventually. See, because we're doing things with this dx, right? If you don't write that dx, you don't maybe remember that you have to substitute in all this for dx. That's a lot to forget. And some problems which are, calculable will become incalculable, if that's a word, right? By not doing this. Anyway, so what is this then? We got what? 2 tangent theta minus 2 theta plus a constant, yeah? And so that naked theta, right? This is a naked theta. It's just sitting there. It's not nothing's covering it. There's no hope but to have an inverse trigonometric function for that, all right? That's fine. Let's write the triangle that corresponds to this substitution. What is it? Let me write it. Let's see. I usually find it profitable to write secant theta. Again, secant theta, excuse me, is 3x over 2, and then I'll just write in words. You know, that's hypotenuse over adjacent, right? Because it's 1 over cosine. So my triangle for this guy, but theta here, my hypotenuse is going to be 3x, my adjacent is 2. Over here you've got square root of 9x squared minus 4. See, I'm lazy. I just go back and look at the problem to know what to put there. But you really should think through it. It's a double check on your substitution, right? Whatever I put here, the Pythagorean theorem should still like be holding, right? Like 4 plus this squared should give me back to 3x if I square root it. And that is the case, yeah. Okay, so what does that make tangent theta in this case? So in view of this triangle, what's tangent theta? Yeah, square root of 9x squared minus 4 divided by 2, right? So I can use the triangle to make this pretty, right? Twice tangent theta is actually what?
Square root of 9x squared.
Right, square root of 9x squared minus 4. All right. Now that 2 theta, it is what it is. We're going to have to make it, it's going to be ugly. But it's not too ugly, I suppose. Minus twice the inverse tangent of the square root of 9x squared minus 4 over 2 plus a constant. So short of some deeper magic, this is the nicest I can make the answer. At the level of our current discourse, that's about the best you can do, I think. All right? Any questions about this? Yep.
If you wanted to make it look nicer, instead of using tangent, would you just use the inverse of secant, which would just be...
Oh, that's true. You do have another option. Oh, very good, very good. Thank you. Like alternatively, you could express this as inverse secant of, you know, twice the inverse secant of what? 3x over 2. Yeah, yeah. That's actually what I was planning to do to start with, and then my eye was just drawn to this formula right here, which made me think, oh, well, the nice formula for theta is also inverse tangent of that, right? Now, which is better? I mean, it depends on your purpose, right? If your purpose is to, you know, calculate this integral, and all you have is a hand calculator to actually plug numbers in, I think the formula I boxed is better because your calculator has an inverse tangent, but your calculator does not have an inverse secant function. I'm stating that with authority, but it's an authority I don't have, as I do not have, of course, knowledge of all possible calculators and all possible hands. Yes?
So you drew that triangle based off the fact that you chose 2 secant theta.
Yeah, I drew that triangle on the basis of, like you said, the initial substitution, which then told me secant was this.
Yes, sir.
So, yep. Okay, so let's get back to basics. Let's talk about completing the square. So if you don't mind, I'm going to give you a 5-minute algebra lesson. All right? I have an axe to grind. And that's that we're not teaching algebra right. All right? In the sense that, how do you factor? Slowly? I mean, if you're like me, you were taught to basically factor by guessing and checking, right? And that's not wrong, right? It's not wrong. So let's talk about factoring for a second here. It's not wrong, but it's a bit unsettling, right? So suppose you're faced with x squared, you know, minus 4x minus 5. Can you factor that?
Looks like it.
Looks like it. We do what? That's x minus 5 times x plus 1. You're like, some of you are feeling like this sense of relief washing over you, like something I understand. This is magical. Do more of this, please. Right? What happens though? You're like, so he's going to make it worse then, right? Yeah, probably. What if I change that to plus 5? Quadratic formula. See, I say all you do is you take half of the middle thing, which is 2, well, minus 2, you square it, all right? So the point of this is when I take half of that and I square it, what I've done, right? What this is x squared, I'll write it out. This right here is x squared minus 4x plus 4, right? So this term right here is identically equal to this. Is that here? It's not, right? So to make the first two terms, here's how I think about it. To make these first two terms equal to this, I can't do, not true yet, right? I have to subtract a 4. Once I subtract that 4, I have made these two terms identically equal to that. That's it. That's completing the square. And then the plus 5 rides along. So what does this tell us? Well, this tells us that x minus 2 squared, that's equal to x minus 2 squared plus 1. That plus 1, what does it mean? What that means is that this quadratic cannot be factored over the real numbers. Your only hope to factor this quadratic is to introduce an I. So you just throw in an I squared like that. I squared equals to minus 1, and then you can factor it. Like that. We can always factor any quadratic over the complex numbers. Right? Let's look at another one. Let's revisit example 4. But in the cold algorithmic light of completing the square. See, because you may not have realized this, but completing the square is easier than factoring. I want you to understand that. Completing the square is easier than factoring. Why? Because it's mindless. There's no guessing. It's just an algorithm. You take half of this, you write the square, you subtract the square of that. I completed the square. That's all there is to it. You take half of the middle term, half of the coefficient of the x, you add that to x, you square it, you subtract the square of the thing you added over here. Now if there's a number in front of the x squared, it gets a little bit fussier, but that's it for these. And what is this? Well, this is x minus 2 squared minus 9. So when you complete the square, there are three possibilities. Either you complete the square, you've got plus a number at the end of it, or you complete the square and you got minus a number. If you've got minus a number, it factors. There's no guessing here, yeah? And how does it factor? Well, this is the pattern, a squared minus b squared, right? So we know that that's a plus b, a minus b. So I can factor it, and this is x minus 2 minus 3, x minus 2 plus 3. And lo and behold, x minus 5, x plus 1. But what's the difference between what I did here and what you guys did at the start? The difference is I didn't guess anything. This factoring was inevitable. It's not a consequence of, oh, can I factor the numbers in such a way and happen to find the sum of things that adds to the thing and product multiplies to the thing, right? There's none of that. Now, is it slower? Absolutely, it's slower, right? What you guys did at the start guessing will beat this every time. But when guessing fails, you should have something to fall back on. And that's what completing the square is. It always works. Let's try another. It works even when you don't know, when it's not nice. So something like this, if I just make up something, x squared, plus 5x minus 10. This one's going to hurt a little bit because what's half of the middle term? 5 halves, right? I got to square that. That gets me back the first two terms. What else does it do? It adds the square of the constant, right? What's the square of 5/2? 25/4, yeah? So I have to subtract 25/4. And I still have that minus 10. Then as a matter of going forward on the factoring process here, and it is going to go forward over the real numbers, right? Because the net number there is negative, so we know it factors. I got to make a common denominator, yeah? So looks like fourths. That's 25 plus 40, 65. So I've got, x plus 5/2 squared minus 65 over 4. And so there you go. That's x plus 5/2 plus the square root of 65 over 4. X plus 5/2 minus the square root of 65 over 4. And I never had to get my calculator out or write down the quadratic formula or any of that. Just direct, efficient calculation. And that's the way to do it. Once you understand this, there's no factoring problem that can stump you. This is what I will try to teach college algebra tomorrow. Wait a minute. Yeah, tomorrow. How do you think it's going to go? Wish them luck. Yeah, well. I mean, guessing is always good, right? And most of the factoring problems you'll ever come to in a math class will allow factoring, right? Because they're in a book which is marketed to people, and a way to make your book sell to other people is to not make it full of problems that students can't do, right? So it's in your best interest to make all of the factoring problems nice, unreal world problems that have all nice integer whole number factorings, But in science and engineering, we do have quadratics which are ugly like that, yeah? And of course, at the end of the day, you want decimals and stuff for engineering. But anyway, does that help for you guys with the completing the square problem? I hope. When there's a number out front of the x squared, just factor it out and then do what I did. Right? Okay, so with that said, the other important thing about my technique is some of you have been taught completing the square in terms of adding numbers to both sides of an equation. This is very short-sighted because the application of completing the square is on expressions. I'm not adding things to both sides of the equation. I am manipulating a given expression to change its form. That's a very different idea than manipulating an equation. Related, yes, but Now, don't feel bad if you didn't know completing the square. I didn't know completing the square until I got to differential equations, actually. It was there it finally hit me. I'm doing things wrong. This is dumb. Why didn't I learn this already? So don't be like me. Because what I would do would be write down the quadratic equation, go solve it with the quadratic formula, and then work backwards to find the factoring, right? Which you can do, but it's just not smart. Much like erasing my last number. Example 6. All right, so let us face Dr. Sprano's final problem. See if we have time. Probably not. We'll give it a go, though. Hey, wait a minute. When's this class end? 10:10. Okay. All right. Here's what we're up against. 3x plus 7 over the square root of x squared plus 4x plus 15. All right, so the way we do calculus on problems involving quadratics, it's pretty much entirely different depending on whether or not that quadratic factors is a product of real factors or if it's one of those irreducible or prime ones. How do you figure out which is what you're up against? Well, you just complete the square. So the first thing we want to do is complete the square on this guy. What's that look like? X plus 2. Yeah, it seems like all of my completing squares, there's this is most of our examples are. And then what? Plus 11. All right, so we skipped the step there. If you want, I can write it off to the side here. So we have x squared plus 4x plus 15. So what I did was I did x plus 2 squared, then I subtracted 2 squared, which is 4. The plus 15 is still there, so that simplifies back to x plus 2 squared plus 11, right?
Yes.
Oh, goodness gracious. I just lost another 10 decipoints. Let's see here, thank you. Now there's two schools of thought here. Well, let me show you a sneaky trick. This will make our life easier. I'm debating. Should I show you the? I'll show you the trick. I'm not sure this is going to help or not. We can debate whether or not this was a good idea or a bad idea. If I've got an x plus 2 here, it's nice to change this x into an x plus 2. How can you do that? How do you change an x into an x plus 2? Little algebra trick here. Check this out. So I do x plus 2 minus 2. See? So that's 3 times x plus 2 minus 6. See that? So this can be rewritten as 3 times x plus 2 minus 6 plus 7, which is plus 1, yeah? I mean, there are different ways to go here. I think it might not be a bad idea to make a substitution before we make the trig substitution, right? You could do that. Let's do that. Let's let u equal to what? How about this? U equals to x plus 2. And then what do we got? We've got 3u plus 1 divided by the square root of u squared plus 11, and dx is what? Is du, right? So how do we integrate that? A tangent? So you say we let tangent, let's see here, is that right? Yeah, I think that's right. So u equals what? You say u equals to square root of 11 tangent theta. I think that's going to do it for us. Let's try it. That makes u squared plus 11 equal to the square root of 11 tangent theta quantity squared plus 11, also known as 11 times tangent squared theta plus 1, also known as 11 secant squared theta. That's nice.